Today our first speaker is Miss Caroline Bertemes. And she's a master's student from ZTH Zurich in Switzerland. And she has been studying the accretion disk around supermassive black holes that shine as quasar. And she has been visiting Center for Astrophysics for a month and collaborating with Dr. Martin Elvis. And she's flying back tomorrow. And starting this fall, she will become a PhD student at the University of Bath in UK. And today she's going to give us a talk on the supermassive black hole.
Thank you for the introduction. So hi everybody, today I'm going to talk to you about applying SDSS color selection algorithm for quasars on models of ultramassive and slowly spinning black holes. So let's recapitulate first of all what we have come to think of as being a normal mass for a black hole within a quasar. We're currently observing masses ranging from around 10 to the 5.5 up to around 3 or 4 times 10 to the 10 solar masses. Now, if we go to the lower mass end, and if we are looking at nearby dwarf galaxies, we can see that the AGN fraction starts to drop to 0.7%. So this is at least an order of magnitude lower than at higher galaxy masses. Of course, one possibility would be that this is a constraint given by nature and there simply don't exist any black holes with lower masses. But on the other hand, Chakravorty et al. Have demonstrated that if we are applying a Keplerian cutoff radius to the broadline region, determined by a minimum velocity of the cloud, and if we assume for this minimum velocity something observationally motivated, like 1,000 kilometers per second, then broadlines just don't seem to form efficiently anymore. So any of these lower mass objects would in fact escape broadline detection. Motivated by that, we had some worries about the upper mass limit. What if this is not a constraint given by nature, but what if there were to be any selection effects of which we are unaware? It would be quite shocking to find out if higher masses existed, because it's already hard enough as it is to try and find a mechanism to form and grow the masses that we currently observe. And these difficulties are illustrated in this plot here from Drackenbrot and Netzer 2012. As you can see, if we look at high redshifts and the most massive objects that we detect, it starts to become very challenging to get them to grow their mass and not take longer than the age of the universe. This is especially difficult if we have a high radiative efficiency, because this means that a lot of the power will just be lost to radiation and can then not be used to fuel the black hole. By the way, all of the small black dots that you can see here are SDSS sources. So this plot also illustrates how much we have come to rely on SDSS, which is why we made the SDSS color selection topic of this project. Let me quickly remind you what effect the mass has on the spectrum. Here I have plotted 2 different Shakura-Sunyaev models. So models of a geometrically thin accretion disk, which consists of annuli, which each are a complete black body. And as we can see, if we go to the higher mass, which is here the dashed line, everything seems to shift towards lower frequencies. This is a direct consequence of the innermost stable circular orbit growing with the mass. And you can also see that in this in this higher mass case, we come to have a real lack of UV ionizing photons. Now, the mass is not all. Spin is also important. And here I have plotted some different spin values, whereas before we just had assumed spin 0. And as you can see, if we go to higher spins, going to the green models, we get more and more UV photons because, again, the spin sets the innermost stable orbit. And for higher spin values, this orbit gets closer and closer to the black hole. So the material radiates at higher frequencies. So there are two different ways in which a source could be lacking UV photons. Either if it has a very low spin, like this violet curve, or if it has a very high mass. Now, besides setting the UV emission, the spin also does some other interesting stuff. For instance, at the highest black hole masses, which had to undergo a lot of growth episodes, probing the spin might help us to be able to say something about the way in which the black hole has grown this mass. Basically, we can consider two different scenarios. If we have one prolonged accretion episodes, or more, but always with the same direction, or mergers, then we would expect to end up with higher spin values. However, if we have a series of just completely randomized accretion episodes, we would expect to eventually reach spin values that come close to zero in a spin-down event. Finally, the spin also sets, in the Shakura-Sunyaev model, directly the radiative efficiency, and I have listed here just the two extreme values. So you see that we can have almost one order of magnitude difference. And this can be very interesting if you are looking at outflows and their effect on the host galaxy. Or, as I have shown you before, if you are interested in the formation and growth of black holes, the radiative efficiency is highly important. Now that you hopefully agree with me that probing the spin can be interesting, let's ask ourselves the question whether SDSS UGRIS filters would actually be able to see any spin effects. And here I have plotted a case study for 10 to the 10 solar masses, Eddington ratio 0.1, inclination 10 degrees. I have used two different redshifts, and for each redshift, two different spins. And as you can see, if we look at the solid lines, which represent the maximally retrograde spin, then the UGRIS filters indeed start to probe this turnover, which goes into the exponential cutoff. So we expect that the spin should affect the UGRIS colors indeed. One further note I would like to add here is that if you are surprised that these models don't overlap nicely in their power law anymore, this is because I have assumed here constant Eddington ratio, which is not the same as assuming constant m dot. Indeed, at constant mass and Eddington ratio, m dot would still be a function of spin, which explains why we have a different normalization for the solid and dotted lines. So let's have a look now at some recent attempts to constrain the spin. Basically, we have two major approaches. One is based on fitting the broad ion K-alpha line. And this K-alpha line originates from the reflection spectrum that is reflected from the innermost regions of the accretion disk. So it gives us a hint of the position of these innermost regions and therefore again of the spin. Now, if you look at the left plot from the Reynolds review paper, you can see that over a vast variety of different masses, we end up with, large error bars because it's very challenging, but also we don't seem to get spin values that really come close to zero. And this is very nicely summarized also in the histogram in the Brenneman 2013 review, which really shows us how much of a trend towards extremely high spin values we seem to have. I'm given to understand that this histogram contains all of the sources from the left plot plus two additional ones. There's another method to constrain spin. One can also fit the continuum, as Drakenbrot did, in order to get an estimate of the bolometric luminosity. This then relates to the radiative efficiency, which can directly be translated into a spin value. And again, we seem to end up with predominantly really high spin values, especially if we go to very high masses. However, before we say now, okay, great, so it seems we have a spin-up scenario, one question that comes to mind is, but what if this is a selection effect? And that was exactly the motivation behind this project. We wanted to verify whether some models with low spin or high masses, which would also induce a lack of EUV photons, would be prone to being rejected by SDSS color selection. And in order to test that, we have generated a grid of models for different masses, different m dot, inclinations, and spins. And we have shifted these to different redshifts and subjected them to the selection algorithm. Here's a quick summary of our grid. So we go from 10 to the 6 solar masses up to 10 to the 11. We go from maximally retrograde spin to maximally prograde spin. We go up to Eddington luminosity. And for the redshifts, we have limited ourselves to redshifts up to 2. Basically because we didn't want to deal with IgM absorption too much. Then we also consider a range of smallish inclinations. So these would appear as type 1 AGN. Now we have two different approaches. On the left plot, you can see the Shakura-Sunyaev model that I already showed you in a previous plot. But then we also use this OpXconf model presented in Doan et al. 2013, which features a color temperature correction. So here in the right plot, we start to get some sort of wiggle in the shape of the SED at some masses, which is due to some photons being Compton upscattered. And this is important in the regime of lower masses and high spins, because that's, again, where the innermost orbit gets closer to the black hole and where we have higher temperatures. Okay, now let's have a look at where our models lie, indeed, in the SDSS color-color plane. In all of these panels, the X and Y axis show you a difference in colors in two different filters. Our models are then the black dots, that is, our models going up to mass 10 to the 9.5. We did not include the higher models, masses here, because we really wanted to compare them to the underlying distribution of SDSS quasars, which is represented by these gray contours. Then you can see some greenish regions and some red regions with an ominous cross on it. These are so-called inclusion, respectively exclusion regions. As you can probably imagine, if you are a model and you fall within an exclusion region, then you immediately get discarded. The algorithm says, no, this is probably not a quasar candidate. However, you can also get immediately selected if you lie within an inclusion region. Now, this was not yet the whole story, because most of these boxes are actually two-dimensional projections of hyperdimensional regions. So in order to be truly rejected, models which lie, for instance, here in this lower panel in the light blue framed rejection region, would also need to lie in the light blue framed rejection region in the other two panels, which they don't. So none of our models get immediately rejected. By the way, all of these boxes are empirically determined, and to the best of our knowledge, they have so far not yet been compared to theoretical models. Now if we go to the upper left panel, some of our models get immediately selected, because there you have this sort of slab with a golden border, which demarks a special inclusion box. It's in fact the only box that is actually just two-dimensional. And let's zoom in on that one for a moment. So this particular inclusion box aims to select all sources that present an UV excess, which is why it selects everything with a U-G color that's smaller than 0.6. And this is regardless of its colors in any of the other filters. Now, for a case study, I have plotted here the position of a 10 to the 10 solar mass black hole, redshift 1, Eddington ratio 0.1, inclination 10. And as you can see, in this case, solely changing the spin can cause this model to fall out of the selection box. In fact, all of our models which have here a spin value that's smaller than around 0.2 are not selected anymore. If you are wondering how this looks like at higher masses, I have plotted here the 10 to the 9 and 10 to the 11 solar mass cases with a vertical offset, since otherwise they would overlap a lot and not be very well distinguishable. But since we are only interested in the x-axis here, I have introduced this offset. So you can imagine, even if we are measuring a source that should normally be selected, since our measurements are not perfect, some reddening could also cause this object to fall out. And how many of our models are falling out is what we have summarized in the following plot. Here we look at bins of different masses and spins. So each of these pixels contains all Eddington ratios, all inclinations, and redshifts ranging from 0.5 to 1. Then the color of each pixel, respectively the number on it, tells you what percentage of these models are selected. If you don't have a color, this means that all of the models in that pixel just lie outside SDSS flux cuts. So we see, if we look at models going up to 10 to the 9.5 solar masses, we find that the selection is indeed extremely complete. It selects nearly all of our models. So this is really a feel-good message. Now let's go to 10 to the 10 solar masses. And we can start to identify a bias against slowly spinning or retrograde spinning black holes. Indeed, the objects lie within this box down here at spin -1 would only be half as likely to be selected as their highest spinning counterparts. And if we go to higher masses, this gets even worse. Now, here you see the same thing for higher redshifts, ranging from 1.5 to 2. And we can identify the same trend. But additionally, if we go to a hypothetical mass of 10 to the 11 solar masses, we also see that the chances of detecting any such object would be practically 0. And that's regardless of spin. So we also seem to have a bias against mass. Now, this was for the models with color temperature correction. If we return to the Shakura-Sunyaev models, this is what we get. The same trends, nearly the same numbers, only some of the highest spin bins change. For instance, if we look at this 82% bin, before it was still at 95%, because the correction is mostly important for high spins. One worry that we have is, what if we have very strong emission lines and these mess with our colors? Here we took a composite quasar spectrum from Vandenberg et al., which we normalized in the relevant wavelength in order to get a relative spectrum. So we could multiply our SDs with that to make them look more like a normal quasar. And this is what we get. Again, we can identify the same trends. There are some strange bins, like for example this light blue 27% bin, where one of the emission lines indeed falls directly within one of the filters. But the general trend persists. Finally, Shakura-Sunyaev models are not really expected to hold at high Eddington ratios, So we have also done the whole exercise using only our models that have Eddington ratios lower than 0.3. And you see, again, we can identify the same trend, but in the high redshift case, things get significantly worse. Look at the 10 to the 10 solar mass column, whereas before we saw a lot of green things going on here. Now we have a lot of blue, which is not good in our color scheme. Also, not only the 10 to the 11 solar mass column, but also the 10 to the 10.5 one are now practically impossible to detect. So let me quickly summarize. Overall, we found a very high completeness as long as we stay at masses below 10 to the 10 solar mass. Then, however, as we go to higher masses, we have identified a bias against slowly or retrograde spinning black holes. And also, if we combine all of our bins at 10 to the 11 solar masses, we find that there would only be like a 3% chance to detect them. So the conclusion is that based on color selection only, we cannot say whether ultramassive slowly spinning objects exist because we would not detect them. Now, I have to say we analyzed just one crucial step. It would now be interesting to know in how far radio and X-ray selection could make up for shortcomings that we found. Also, we have limited ourselves to lower redshifts. If we go to higher redshifts, SDSS criteria change, and we cannot say anything about the completeness there. Finally, not finally yet. A lot of our models have also just dropped out of the selection because they lie outside of the flux cuts. So it will be interesting to see how future surveys might be able to detect a lot of more sources due to a lower flux cut, like Subaru, for instance. One thought was also that I have shown you this wiggle introduced by the color temperature correction. Could we maybe use the slope of this wiggle to specifically search for retrograde spins? And finally, even if a model gets color selected, that does not mean it's classified as a quasar. It then has to undergo a spectroscopic follow-up, and emission line diagnostics will tell us whether this is probably a quasar or not. And currently, I am investigating the completeness of these emission line diagnostics. I'm taking the models that I have just showed you of the continuum emission, which I then let run through the photo-ionization code Cloudy, which gives me back spectral lines. And based on these, I hope we will find out something interesting about whether models are selected or not. Thank you for your attention. Now, do you have questions?
In the iron line spin measurements, there seems to be a very, very rough indication that for the highest mass you get lower, you tend to get slightly lower spins. What you're showing here is it the opposite to this? It looks like you're going in the opposite direction. Do you think?
Yeah.
Do you think it's because of a bias effect, an observational bias, or is it an actual?
So before, I think our results are maybe not really consistent depending on which method we choose to look for high spins. So if we use this continuum fitting method, then at higher masses we actually seem to get higher spins. Yeah, right now posing any constraints on the spin is still very challenging. So we do have a lot of controversy there.
I might have missed that. Do you introduce noise in your models?
No, we have not considered noise right now.
So it could be even like...
Yeah, it could be even worse. If we have dust, it will be worse. If we have host galaxy contamination, it will be worse. Yeah.
I was just going to say that the spins hit the one line there, just where the cutoff comes, 10 to the 10.
Yeah, that's right.
So it could indeed be a selection effect.
Mm-hmm. Yeah, with this plot, it really fits well.
I may miss some of the numbers, but even at a fraction of a percent chance of finding something, why wouldn't you find plenty in the Sloan survey?
Well, it already becomes challenging for us to have models that fall within the flux cuts, that have a very high mass, but have a magnitude that still falls within the flux limits. So what my colorful plots from before don't tell you is how many sources you would still have that fall within the flux cuts. Indeed, I think there were only like 12 or so left in this regime. I checked it once.
Another question?
Can I ask a second one? Are you worried at all about warm absorbers?
No, we have currently also not worried about warm absorbers because we think this would also diminish the radiation again.
Any other questions? If not, let's thank Caroline. Our second speaker is Dr. Ashkbiz, Danehkar, and he's currently a postdoc fellow and speaker for astrophysics. And he joined here last year. He got his PhD from Macquarie University in Australia in 2014. He got his master's degree from Queen's University in Belfast, UK, in plasma physics. He got another master's degree in computer science from University of Rostock in Germany. And he is an expert in AGNs and stellar astrophysics. And he's going to give the second talk today.
What is this? Oh,
The
this
mic,
is
if
microphone.
you like. Sorry, I forgot. Okay.
Thank you for your introduction. I would like to thank everyone for giving me an opportunity to come here to talk about my research here today. Today I am going to talk about ultra-fast outflow in active galaxy nuclear of Safer-1 galaxy. My talk mainly is a literature review of recent results, and at the end I will talk about our recent observation with Chandra-Gratin spectrograph. Here I am working with Julia Lee and Mike Novak at MIT and Randall Smith at CFA, and also I work in collaboration with other researchers. Large-scale ejection have been detected in radio-load AGN, while radio-quiet AGN mostly show a small-scale radiative-driven winds. It is really Chandra and XMM made it possible to see this small-scale radiative-driven wind. And in Safer-1 galaxy, we have the view to these central regions. Here, the outline of my talk. I will talk a bit about what is the classification of AGN based on Unified model. And I will talk about what is ionized X-ray absorber in AGN. And I will talk about two different types of ionized absorber in AGN. one of them warm absorber, another one ultra-fast outflow. And I will explain how we can constrain physical condition of ionized absorber using photoionization modeling. and also I will talk about possibility of unification, warm absorber, and ultra-fast outflow using a density, unique density profile. And also I will talk about, I will present our latest result of our group with recent Chandra-Geratin observation of PG1211. About nearly 15% of nearby AGN are classified as a radio load, while the rest are classified as a radio quiet AGN. This radio quiet AGN divided to two different groups. One of them are safer 1 and another one safer 2. In safer 1, it is very bright in X-ray and ultraviolet observation, and while safer 2 are very bright in infrared observations. This suggested that the safer 1 and safer 2, we are seeing them from different inclination respect to line of sight. And the safer 2, we are seeing them from low inclination, while safer 2, we are seeing them from high inclination. And the safer 2, we don't have any view to central region, and central region are blocked by dusty torus around a supermassive black hole. And this unified model have been developed nearly 2 decades ago. In terms of what we learn from X-ray observation of AGN, we learn about thermal soft axis, which usually modeled by a black body, and we learn about non-thermal axis of X-ray observation, which related to corona above accretion disk, and this hard axis usually modeled by a power law. And we learned that there are some warm absorber, and which could be related to outflow above accretion disk. And here you see this is a phenomenological model of X-ray observation. This is the black body which related to this region, and the power law related to this region. And warm absorber is this component which usually observed in soft band, and also we have warm absorber iron which we observe in around 7 kV. There are two types of ionized absorber. One of them historically called warm absorber, because first we observed them in less than 2 kV. And historically it was only magnesium, silicon, and sulfur and oxygen which show this warm absorber, and later we see them in iron. And right now warm absorber phrase is used for those ionized absorber with velocity less than 10,000 kilometer per second, and ultra-fast outflow are those warm absorber with velocity much higher than 10,000 kilometer per second, and some of them reach the velocity of 0.1 to 0.4 speed of light. And warm absorber recently observed in nearly half of safer 1 galaxy, while the ultra-fast outflow have been observed of 30% of radio quiet and radio load AGN. Here are the list of well-studied safer galaxy. As you see, the ultra-fast outflow with a speed of 0.1 and up to 0.2 speed of light seen in mostly in safer 1 galaxy. And we also notice few of them as a redshift absorber. This blue shift absorber could be related to outflow toward us, while redshift absorber could be related to infall of matter to supermassive black hole. To study physical condition of a warm ionized absorber, we use a phenomenological model. The first two component, black body plus power law, model continuum of X-ray observation, while this component, photo emission and ionized absorber component, are used to describe the emission and absorption of ionized absorber. There are two different methods for fitting warm absorber and photoionization, one of them using X star dB, another one using X star to expect or X star to table. And these two methods are very computationally expensive and require a special technique. Recently, I worked on parallelization of MPI using MPI because previous tools was made with PVM, and recent supercomputer doesn't support PVM and mostly support MPI. And using MPI X star, we are able to run a parallel of X star for different free parameters. Usually the free parameters are column density and the ionization parameter. And we can make a grade of a X star table model for different, a range of column density, for example, from 19 to 25, ionization parameter from 0, logarithmic ionization parameter from 0 to 5, and we can use, for example, expect or ISIS to fit which column density and which ionization parameter are best produce the physical condition of ionized absorber. The fundamental parameter in photoionization modeling of ionized absorber are ionization parameter and column density. Ionization parameters are defined by this equation where L is luminosity, ionized luminosity. Ionized luminosity in X star usually defined by luminosity integrate from 13.6 electron volt to 13.6 keV. And R is distance from ionizing source, and N is gas density. And column density defined by this equation where delta R are thickness of ionized absorber. And using these two equations, we can constrain upper limit of ionized absorber, while lower limit can be obtained by this equation where m is mass of supermassive black hole, and this velocity is maximum outflow velocity, which can be observed in AGN. Here we see the range of parameter for a sample around 42 radio quiet and 41 AGN from literature. From this paper, you see this is the result for ultra-fast outflow. As you see, the ionized absorber are in range from 2.5 to 5.5, and the column density are in range from 21 to 24. The red line describes the lower limit, and the black line here describes the upper limit of column density. And here you see the range of outflow velocity where ultra-fast outflow have been detected. As you see, it is in range from 0.1 to 0.2 speed of light. Here you see the result of photoionization modeling of NGC 4051. In this paper, they model different warm absorber using 6 different absorber components. And here you see the plot of ionization parameter versus outflow velocity. As you see, there is a linear correlation between the ionization parameter and outflow velocity. When ionization parameter are low, the outflow velocity are very low, and where ionization parameter, which is high, and usually it is on iron, the outflow velocity reaching 10,000 kilometers per second. And this linear correlation suggested this view of AGN. Here there is shock from accretion disk around supermassive black hole, and in this region, which mostly we observe in X-ray hard band, we see this very high ionization where the speed reaching 0.1 speed of light. While in this surrounding region where the temperature is cooling and the speed of a gas is slowing, we see this component where ionization parameter also is lower. So this correlation suggested in this quasar we could have this schematic view of shock wind model. Another important parameter in ionized absorber is density profile of ionized absorber. Density profile of ionized absorber usually studied using a method called absorption measurement distribution, AMD. These methods are similar to emission measurement distribution. Absorption measurement distribution is defined as a distribution of column density with ionization parameter. Assuming a power law for density profile, using AMD, we can determine this index, power law index, and from here you see the result for 5 AGN, and using this correlation, the Behar obtained this index alpha is in range from 1 to 1.3. Recently, Tumbasi studied around 35 AGN, and he found that this index are in range roughly about 1.4. And here are blue are ultra fast outflow, and red are warm absorber. So the warm absorber has usually a speed less than 10,000, and the ultra fast outflow has a speed more than 10,000 kilometers per second. And this density profile suggested that ultra fast outflow and warm absorber could be related to one phenomena in AGN. And for example, warm absorber from outer region and ultra fast outflow from inner region. Here you see there is a correlation between ionization parameter and column density. And at the bottom, you see there is a correlation between ionization parameter and outflow velocity and column density with outflow velocity. And Tumbasi, using this correlation, suggested that the warm absorber and ultra-fast outflow are related to a singly large scale outflow with power law density profile, and they could be related to the same physical system. However, there is another study. In Tumbasi, they study around 35 Cipher 1 galaxy. Here they study around 26 Cipher 1 galaxy, and some sample is the same as Tumbasi sample. But here they use a spectral energy distribution for photolonization modeling, and they found that the correlation between ionization parameter and column density for ultra-fast outflow and warm absorber are not consistent with each other. They suggested that the warm absorber and ultra-fast outflow could not be related to the same systems. In these two papers, they use two different methods. Here they use power law, but here they constrain spectral energy distribution of ionizing source. Now I am talking about our recent result, which obtained with Chandra grating spectrograph. We observed PG1211, which previously observed with XMM Newton. Pound in this object have been observed several times with XMM Newton, and since 2003, pound have been detected outflow velocity with 0.08 speed of light. And this outflow velocity have been detected in several warm absorber of carbon, nitrogen, oxygen, neon, sulfur, and iron. And also there is some paper which they claim that there is infall with redshift between 0.2 and 0.4 speed of light. And recently, Pound claimed that there is two-component outflow velocity, one of them 0.14, another one 0.07 speed of light. However, there is two other papers. They use one of them, one of XMM Newton, which already studied by Pound, and there is another paper recently, which they use new star observation, and they contradict the result which found by Pond, and they claim there is no ultra-fast outflow. Our recent observation done by Chandra grating spectrograph, and we use 430 kilometer second exposure, and our observation done by 6 observation over 9 days. And as you see, most of our observation in low state. One of them, it is in high state, in bright state. And here there is a hardness ratio. We wanted to see if all observation, if there is any change in hardness ratio in all observation. As you see, and there is a very minimal variation in this observation. And in order for our study, in order to make our study very consistent, we excluded this 4 observation because it is in very bright state. And the warm absorber are very strong when it is in very low state. So we combined this 5 observation, and we did a time average study. In order to make our photolonization modeling, we construct a spectral energy distribution. Our observation was simultaneously with radio observation and HSTC observation. We use our radio observation and HSTC observation and archival infrared and optical data together with our Chandra observation, and we made a spectral energy distribution. And using this spectral energy distribution, we made this component, warm absorber and photon emission, for fitting the time average Chandra grating observation. Here you see the spectrum of Chandra observation. The red line is a fitted model, did it using a blind searching code. As you see, there are several component ionized absorber here. And we found that this component has velocity of 0.06 blue shifted. So this component could suggest that there is a ultra fast outflow in PG1211. And here you see the iron emission from K-shell, from natural region far from the central region of AGN. One of the important issues in fitting ionization parameter is the thermal stability of the ionized absorber component. Thermal stability of ionized absorber can be studied using an effective theoretical tool called stability curve, in which the gas temperature plotted against the pressure. When the slope of this curve are positive, the gas in this region are stable, or they are in thermal equilibrium. This means cooling and heating are in balance. So in this thick blue region, the gas are unstable. So the absorber component could be exist only in this region, not in this region where are unstable. So for photolonization, we use this theoretical tools to constrain the warm absorber. Right now, the warm absorber, we fitted only one component warm absorber, which is here. If there is iron, it could be here. Because the iron only exists in this region, while other components can be exist in this. This is a plot of ion fraction. We plotted. This is this temperature. This is helium-like, hydrogen-like, neon, magnesium, silicon, and this is ionization parameter. And this ion fraction, as you see, the ion fraction, for example, for neon, magnesium, silicon only exists when they are stable, when they are in this region. But for iron, it is only in this region, which means that they have the ionization parameter more than 4. Here is a summary of my talk. Just to conclude, the warm absorber and the ultra-fast Otpolo are seen in Safer 1 galaxy. The warm absorber are those with velocity less than 10,000 km per second, while ultra-fast Otpolo are with velocity more than 10,000. To constrain the physical condition of ionized absorber, we use photoionization modeling, and the free parameter in photoionization modeling are ionization parameter and column density. And in order to make photoionization, we make a grade of photoionization models, and we fit this photoionization model and spectrum to find what is the best ionization parameter and column density. And using this method, we can determine what is the density profile of if there is any unification of ionized absorber, what is the density profile of this ionized absorber. And I also present the latest result of our Chandra grating observation, which suggested that there could be the ultra-fast outflow with 18,000 km per second, 0.06 speed of light, which is consistent with Pound recent paper. Thank you for your attention. I am happy to answer questions.
What sort of mechanical power is being carried in these ultra-fast outflows?
There are different theories. One of them is a magnetic hydrodynamic theory, which, as you see, there is a simulation using magnetic hydrodynamic theory, and as you see, it's reached the speed of 0.1 speed of light. Other theory could be frame dragging relativistic theory, but this is not relativistic theory. This is magnetic hydrodynamic theory, and using magnetic hydrodynamic theory, in this paper they study quasar, and they found that it reached this speed, which is consistent with observation. So this jet could be powered by magnetic hydrodynamic energy of the accretion disk, or could be related to angular momentum energy of black hole.
But from your observations and model, can you estimate the number, the amount of power? This is the mechanism, which is...
Yes. For a fitting model, we can only find what is the best for the fitting photoionization modeling, and unless the observation, we can only find what is the best ionization parameter and column density. So we couldn't find what is the energy which driven this jet. This is the work which should done with theoretical modeling. Yeah.
A couple of questions. In your stability curve, was that for solar abundances?
This is, yes, for solar abundances.
Yes, so if you go to higher abundances, the wiggles get larger, and you get less stable regions.
Yeah.
And the abundances in quasars and AGN are typically a few times solar. So you'll find when you do it, that they wiggles are much bigger. And this is in another paper by Chakraborty et al.
Yeah, it's interesting point.
And the other one is how you do the line identification. Is it you go through finding features and then identify them with a line?
And we use a Gaussian absorption model.
How do you find a line and give it has an energy or a wavelength, and you say, okay, that's best matched to some particular line.
Yeah, we use a series of hydrogen-like and helium-like lines, and there is, for example, 4 lines each.
So the problem with this approach is that the resolution of the gratings that we have, you've got a lot of line blending. If you do a full model of a photoionized region, a large fraction of the lines are actually blends of more than one line. How do you deal with that?
Because we use the helium-like and hydrogen-like, it could be some line blended. But because the helium-like and hydrogen-like are very strong, as you see, this is the feature which is silicon, and this is the feature of magnesium. And it could introduce some uncertainty when there is blinding.
Is your density profile related to cloud distribution or just a smooth medium?
Pardon?
Is the density profile measured as clouds per unit volume or just density of the smooth medium?
This density profile, you are talking about this density profile.
Yeah.
This density for the number density, but the column density is the density which is unit centimeter to -2. But this number density has centimeter to -3, and from this AMD we can plot and find what is the distribution of this number density.